Section 9.1, Sequences. A sequence is just another function where the domain is simply the set of positive integers. So that means obviously whenever we talk about what expression we're plugging numbers into, like we do with functions, we're only going to be plugging in 1, 2, 3, and so on. So really maybe instead of saying positive integers, we can just say the natural numbers. So the domain obviously is going to be 1, 2, 3, and so on, all the way up to whatever number we may want to think about. Now, when we talk about what the terms are, the way we like to notate it would be that when we plug a 1 in, we'll call that the first term in the sequence. Generically, we like to call it a sub 1. When plugging in our second number, we get a sub 2 and so on. And these represent all the terms in the sequence, all the way up to some a sub n. Now, it's important to understand, however, sometimes, every so often, and it kind of depends on the expression that defines the sequence, that you may sometimes start at 0, but primarily, as just a general rule, we like to have our sequences start at 1. So for example, if we have a sequence defined by a sub n equals n plus 1 divided by n, and we wanted to list the terms of the sequence, again, we would just be plugging in a 1, 2, 3, and so on to see what that would look like. So in this case, this sequence, if you were to lay it out, would look like 2. That's when you plug a 1 in. When you plug a 2 in, you'll get 3 halves. When you plug a 3 in, you'll get 4 thirds, and so on. And it just kind of keeps going for as long as you'd like to do. Now, some sequences have different things than just plugging in numbers. For instance, when you take an expression and multiply it times -1 raised to a power, what happens is that as you lay those terms out in the sequence, you're also multiplying each one by -1, where sometimes it's being raised to an even number and sometimes being raised to an odd number. Well, obviously -1 raised to an even will always be +1, where -1 raised to an odd number will always be -1. So when you look at the terms of this sequence, yes, the numbers themselves are generated by the n squared plus 3, but they're going to be alternating signs. Because it is just an n up here in the exponent, when you plug a 1 in, it's going to put a negative in there. Okay, so in this case, again, laying out the numbers of this sequence, if you want to see the first 3 or 4, so on, would work out to be when you plug a 1 in, you'll get -4. When you plug a 2 in, you get +7. When you plug a 3 in, you get -12. And when you plug a 4 in, you get +19, and so on. Now, if you wanted to have a sequence that maybe started positive and then go negative and kind of alternate which one these are, you could easily do that by taking the exponent here and making it n plus 1. That would change when you have the even and odd, exponents for the -1. Now, another scenario that sort of accomplishes the same sort of thing is if we, for instance, defined a sequence with a trigonometric function. Now, here I am just going to be plugging in 1, 2, 3, 4, and so on, but because of the values of cosine, at intervals of pi over 2, sometimes you have 0, sometimes you have 1, sometimes you have -1. So this is a different kind of sequence. So here, if you plug a 1 in, you'll just get, the cosine of pi over 2, that's just 0. When you plug a 2 in, you'll get the cosine of pi, so that's just going to give you -1, and then 0 at 3 pi over 2, and then +1, and so on. Okay, go back to 0. So this is another type of sequence where, again, because it's kind of defined trigonometrically, we get a different sort of pattern. Now, other types of sequences are defined what are called recursively. Now, what this means is that in order to find a given term in the sequence, you have to know one or maybe more of the first terms. So essentially what's going on is that the next term in a sequence is found and defined by whatever the value of the one previous is. Now, the sort of notation that you would get in order to generate this looks like this. They're going to give you the general rule. Now, that basically says that a of n sub 1, the next term, is equal to twice a sub n, which again is the previous term before that, plus 5. So that means any given term in the sequence is equal to twice the term before it, plus 5. Now, obviously, in able to get this, thing rolling, we have to give you that first piece of information. So obviously, in addition to writing the rule recursively, they have to give you an initial starting point. So in this case, if I wanted to list the terms of this sequence, I would start at 5. That would be my first term. So we'll start with 5. And then again, to find the very next one, I'm going to take 5, in this case, double it and add 5, and then keep doing that idea. So the second term is going to be 2 times 5 plus 5. Okay, so in this case, when you do that, you can get 15. Okay, to get the next term in the sequence, now we'll do the same idea, but except this time with 15, because that's the term right before the one I'm trying to find. So if I take 2 times 15 and then add 5, that's going to give me 35. Okay, and then again, to find the next term, I'm going to double 35 and add 5. So in this case, it'll equal 75, and so on. So a recursive function, again, just kind of has a little bit more complicated rule, because obviously to calculate any given term, you have to know the one before it. But more importantly, it has to give you that initial number to start on, so that way you know exactly how to get those first terms going. Now, another example of this could be maybe where you have the rule, but this time the recursive is actually involving the two previous ones. So in this rule, any given term in the sequence, right, is equal to 3 times the term 2 before it minus twice the immediate term right before it, okay? So we're going to call n plus 2 what we're trying to calculate, which means n is 2 terms before that, and n plus 1 is 1 term before that. So in this case, as you can see, we need to give 2 pieces of information to get it rolling because it takes the 2 previous terms of the sequence to generate every term in this one, okay? So in this case, if we wanted to list them out, obviously the first term is 6. The second term is 3. Now, in order to find the third term, we're going to triple the 6 and subtract twice the 3, to get that next term. Now, doing that is going to give me a 12. To find the next term, now we're going to triple the 3 and then subtract twice the 12, okay? And doing so then gives me a negative 15 and so on. So recursively defined sequences don't just have to involve a term and maybe the one before it, but could involve any number of terms. So I've given you an example here where, again, we have to know the previous two to generate any given term in that sequence. Now, sometimes we want to be able to generate our own rules, okay? So we may be in a situation where we have a sequence, right? We can see the numbers, and at least enough of them to get the idea, and we want to write what that general nth term looks like, okay? So our job is to write that rule. Now, depending on what type of the sequence you have, there's different things you want to think about to make it happen. So some hints could be look for differences. Is it going up by the same number every time? Maybe look at powers, right? Could these numbers be generated by raising different numbers to different exponents? Okay, those are things you want to think about. But generally, you're looking for any sort of rule that when you plug a 1, 2, 3, and 4, it generates these numbers. And sometimes that's a really nice way to start. Ask yourself, what can I do to get this number when I plug in 1, this number when I plug in 2, and this number when I plug in 3, and so on. And sometimes that can help guide you. Now, always, and depending on how you write them, to be clear, there oftentimes could be more than one rule that may work. So to give an example, let's look at this one, 1, 6, 11, 16. Now, what I notice about this one is that we go up by 5, up by 5, up by 5. And since we keep adding 5 over and over and over again, that's kind of like the definition of multiplication. So what my mind thinks is this is going to be 5n, because clearly having 5n, multiplication, jumps you up by 5 more over and over and over again. Now, the issue, of course, is that if I stick with just this and plug a 1 in, I'm not at 1. Right? I'm at 5. So what we can do here is say, all right, this is going to make me jump up by 5 every time, but I'm going to add a little bit more to make sure I start at 1. Because again, when I plug a 1 in for n, I want the value to start at 1. So because right now plugging 1 in gives me 5, if I simply subtract 4, it basically takes that sequence and shifts it back 4 to begin at 1. Now, anytime you feel like you have the answer, always, double check it. Plug a 1 in, a 2, and a 3 and see if it works. So if I plug 1 in, 5 minus 4 is 1. If I plug a 2 in, 10 minus 4 is 6. Plugging a 3 in gives me 15 minus 4, that's 11. And again, if we kept going, this one does check out. Now, in this example, we see a couple things. First off, 4 to 8 to 12 to 16, just like our last example, is jumping up by the same number every single time. So ignoring the whole plus or minus part of it, I'm going to do kind of the same thing I did last time and say that, to begin this process, clearly it's going to go 4n, okay? Now, I don't need to really adjust because the first number is 4, the second number is 8, the third number is 12, so 4n really does generate these values. But as you can see, like we previously looked at one of our initial examples, we have that alternating sign. So what I need to do, like that initial example, is take the 4n and multiply it times -1 raised to a power. Now, it's important also to stop and think, do we want the first, third, fifth, and so on, do we want them to be the negatives, or do we want the second, fourth, sixth, and so on terms to be negative? Now, in this case, we want the very first term and third term and so on. So keeping n just as n up here in the exponent is going to make the first and third and fifth into a negative. If this had been 4, -8, +12, -16, I would use an n plus 1 in the exponent to generate that sequence. Now, in this example, we have a 1 and then a 2 and then a 4 and then an 8, and this isn't jumping up by the same number every single time. But what I am noticing is that to go from 1 to 2, we doubled it. 2 to 4 doubles, 4 to 8 doubles, okay? Now, if we add the same single number every single time is the definition of multiplication, then if we multiply by the same number every single time, that's the definition of exponential. Because if you keep multiplying, in this case, by 2 over and over and over again, that's generating those terms. And obviously, if you want to multiply by the same number over and over and over again, you'll raise it to an exponent. Now, in this case, I'm just going to start with 2 to the n and make sure it definitely generates these things. Now, obviously, in this case, if I plug a 1 in, I'm at 2, right? And if I plug a 2 in, I'm already at 4, and I'm kind of missing that initial term. So there's a couple things to think about. First off, if you want to go ahead and assume maybe that this sequence begins at 0, right? You want that to be your first term. And sometimes, again, with sequences, we can do that. That's not a problem. We can stick with this, okay? And again, normally we start at 1, but it's not always an issue if we need to start at 0 for whatever reason. Now, we can't use negatives, but 0 could be fine. Now, if you're someone who wants to make sure that this sequence does start at 1, then clearly an easy way to do that would be simply to take the exponent and make it n minus 1 and shift it back. That way, when you plug in a 1, you'll get that 0 power to give you 1. And then when you plug in a 2, it'll take you to the first power to give you this as the second term. So we have a couple options there. I like to always think, obviously, starting at 1 as often as possible. But again, just be flexible. There will be situations where the sequences we're talking about are going to need to start at 0. Now that we've talked about sequences and kind of writing their rules, one of the most important things that we're going to be looking at here in this entire unit is the idea of either something converging or diverging. Now, in terms of a sequence, if it approaches a certain value, like it's closer and closer and closer to this certain number, then we say that it converges to it, okay? And we're looking at is saying that, n is becoming larger and larger and larger. As we, evaluate the sequence and look at more and more terms, if it's, going to a number, we say that it converges to that number. Now, it doesn't actually need to get there. It just needs to be getting closer and closer and really infinitely closer to it. Now, if it's not really approaching a number, perhaps it just gets smaller and smaller and smaller or bigger and bigger and bigger without bound and not really going anywhere, then we say it's divergent. Okay, so those words are going to be very important vocabulary for this entire unit. Now, one way we can look at that is to simply write out the sequence and get a sense of kind of what's going on. Now, in this example, we have 1 over 2 to the n. Now, in this case, if we look at the terms of this sequence, this is basically 1/2, and then 1/4, and then 1/8, and it just continues on like this, where the denominator keeps doubling and doubling and doubling, while the numerator always remains 1. Now, as we keep looking at, larger and larger values of n and what terms in the sequence they generate, it's pretty clear to see that these numbers are definitely getting smaller. Now, the thing about these numbers, of course, though, is that even though they continue on this pattern and the denominator continues to get larger and larger and larger, it's never actually going to get to 0. It's never actually going to get negative. But clearly, looking at the size of the numbers themselves, they're approaching 0, much like a limit. So in this case, our conclusion for this one can say that this sequence converges to 0. Even though it may never get there, again, as n becomes infinitely big, the terms themselves are getting infinitely close to that value 0. Now, oftentimes to do these, as we kind of got a feel for in that initial example, we do what's called the limit of the sequence. And this is nice because it allows us to use our previous experience with limits on sequences. Now, remember, a sequence is still just a list of numbers with commas between them, but they are still operating like a function. We have inputs and outputs, and we can talk about where those values are going and what their values are as we increase larger and larger values of n. So this limit at infinity, right, as n approaches infinity, can go to a number. And again, like we talked about, if it goes to a number, the limit exists. Now, clearly the limit does not exist, right? If we look at larger and values of n and it doesn't really go or converge to a number, then clearly it's going to diverge. This just offers us quicker, nice methods to figure out when we have a sequence that converges. So we get to use that previous experience with limits and really apply them to a rule, kind of like treating it like a function. So for instance, here in our first one, we want to determine, does the sequence defined by n minus 1 over n, does it converge or diverge? Well, we're going to do the exact same things we did before, right? We're going to figure out what that limit looks like. So we're going to treat it just like a function, right? So we can, even though this doesn't have the same type of outputs as a function, it's behaving in the same way. So what I can do is basically say, what is the limit as n approaches infinity of the a sub n? Well, just like I did with functions, this is rational, and when n becomes infinitely big, the way we figure it out and look at it is we look at those leading powers, right? So on the top it's first degree, the bottom is first degree. Because they're the same, this expression basically goes to and approaches the coefficients, in this case 1 over 1. So because the limit of this expression equals 1, we can say that it converges to 1. Now, this example, we basically have the same idea, but of course it looks a little bit different, okay? So we're going to apply the same sort of rules and do the same sort of thing. And again, when we ask ourselves, what is the limit as our terms become infinitely big, again, we still have that same power. So because the coefficients are 1, that means that this expression, again, is going to 1 and therefore converges. Now, what you'll discover in this unit as we do more and more of these is that it's more important to know whether it converges or diverges, and less important is, oftentimes as what specific number it is. Right now, we should definitely get both, but down the road, what you'll discover is that knowing whether something converges or diverges oftentimes is the most important piece of information. Not so much the value, maybe like we were discovering in limits, but obviously the fact that the limit exists tells us clearly that it is going to happen that way. Now, in this next example, I wanted to throw in some factorials because, in this unit, as we look at sequences and some series and other things coming up down the road, we're going to see factorials happen a lot. So I just want to, from day one, really get used to working with these and understanding how they behave. Now, in this case, obviously, we still want to let, this have larger and larger values of n, but because it's a factorial, we got to be a little careful and understand exactly kind of what's happening here to understand exactly where it goes. So sometimes, especially with factorials, we may want to simplify. So now, again, we're going to be looking at the limit as n becomes infinitely big, and the top, of course, is n plus 1 factorial, which is getting, really, really big, but then again, so is the bottom, right? Obviously, n factorial does the same thing. We want to figure out where it's going to go. So just like with all limits, right, we want to get a handle on what's happening. We can't really apply the previous rule because those are with polynomials, and these are not polynomials. So what we're going to do is we're going to simplify it. Now remember, factorial just means that you're multiplying times n, times 1 less, times 1 less, times 1 less, times 1 less, eventually until you get to 1. N plus 1 factorial means that you're multiplying times n plus 1 times 1 less, times 1 less, times 1 less, right? So what we can do in this case is we can rewrite n plus 1 factorial as n factorial times n plus 1. Because again, what that is doing is saying this is n plus 1 times n times 1 less, times 1 less, times 1 less. Now the reason we want to do this, of course, is because now when I write it this way, I can see clearly that the n factorial on top and the n factorial on bottom, those are going to reduce. So algebraically, I can say that this is really going to be the limit as n becomes infinitely big simply of n plus 1. Now, looking at the values of n and in this polynomial, if n becomes infinitely big, these just grow and grow and grow and really approach infinity, right? The numbers just continually increase without bound. So this right here is going to infinity, and clearly that means the limit doesn't exist. Since the limit doesn't exist, then the conclusion we can make about the sequence is that this sequence diverges. Now in this case, same sort of problem. The only difference, of course, is that while we want to really stick with using our limit ideas and our experience from that part of calculus, we were not given an expression or a rule. So to do a problem like this, it's easy to simply write a rule first, and then once you have the rule, then we can do the sort of things we're looking at, okay? So first off, let's write the rule. So the first term gives us 2, the second term gives us 4/3, and third term gives us 8/5, and so on. Now one thing I like to do, especially where we have a lot of fractions in there, is make sure that every single term in the sequence looks like a fraction. So we do have a 2 here, but remember that's the same thing as 2 divided by 1. And I think that's helpful because if I want to write the rule for sequences where I got lots of fraction terms, it's very easy to focus on the numerator and denominator separately. So the first thing I'm going to do again is figure out what's a nice rule that would define this sequence. So what I notice on the top, and just looking at the top, we have 2, 4, 8, 16, 32, and so on. So it looks like we're starting at 2 and then doubling and doubling and doubling and doubling. We sort of saw that in a previous example. So my numerator could be described as 2 to the n. Now on the bottom, we just have 1, 3, 5, 7, 9. It looks like we're just doing odd numbers. Now, technically, when you want to describe odd numbers, they're all 2 apart. So the first thing I want to mention is we're going to go up by 2, up by 2, up by 2. So again, just like some of our previous examples, that'll be 2n. But we want to make sure we start at 1, so I'm going to subtract 1 from that. Now, instead of looking at our list of numbers here, it's a lot easier than to look at the rule because then we can try and do some calculus. So in order to figure out whether this converges or diverges, we'll be doing the limit as n becomes infinitely big of this rule. Now, the thing is, and I'm going to go and write this in here, this isn't, again, a polynomials, right? We can't just apply the idea of exponents and powers and things like that. Instead, we just have to figure out, and think about what each piece is doing separately. So clearly in the numerator, if you have 2 raised to a power and you just let that power become bigger and bigger and bigger, the numerator is going to become infinitely big. And certainly the same can be said about the denominator as well. So in this case, technically doing the limit on this would be in an indeterminate form. So therefore, we can use L'Hopital's rule. So that means to figure out this limit, we can let, again, n approach infinity, and then by applying L'Hopital's rule, we'll just differentiate the numerator and denominator separately. So we look at the derivative of 2 to the n. That's, of course, 2 to the n times the natural log of 2. And we'll divide that by 2, because that's obviously all that's going on there. Now, in this case, again, going back and trying the limit again, the denominator remains 2 all the time, and the numerator just grows without bound. So in this case, what we can say is that overall, the terms are just increasing without bound, and therefore goes to infinity, which again means the limit doesn't exist, and therefore the sequence diverges. Now, the last thing I want to talk about is the idea of a monotonic sequence. Now, obviously, down the road, we're going to be looking at some more complex things, and the big question on our minds will always be whether something is increasing or decreasing, so on, but more importantly, whether it converges or diverges. And knowing whether or not a sequence is monotonic really helps us do that. So just to define this, a monotonic sequence means that the sequence essentially is always doing the same thing. So one option could be that's called a non-decreasing sequence. And that simply means that from one term to the next, you're never getting smaller, right? So either you're going to stay the same size or the next term is going to be bigger. You're never ever decreasing. If that's the case, we can describe it as being monotonic. It'd be said to be monotonic decreasing or non-decreasing because it never gets smaller. Now, the opposite can also be true in a monotonic sequence. In this case, one that always decreases, right? From one term to the next, we're either the same or getting smaller. And that would be called non-increasing. Now, again, it's important to know that because if we want to know as the values in our sequence become infinitely big that it's going someplace, we always want to know it's going in the same direction, right? In this case, if it's non-decreasing, it's sort of always going up. Or if it's non-increasing, we know it's always going down. Now, in addition to knowing whether it's always going up or down as far as those sequence terms, knowing whether it's bounded actually answers that question. Because if we know that we're always increasing, but yet never going above a certain number, right? That means we're bounded above by this number. This would be called our upper bound. That would tell me that, therefore, it's going to definitely converge to that number. That's our theorem. If we're bounded, we know we never get bigger than a number, and we're always increasing, it converges. And the same can definitely be said if you're bounded below by a number. If our terms are non-increasing and therefore always getting smaller, but yet we never go below a certain number, we're bounded from below, again, that's going to be enough evidence for us to say that this sequence converges. Okay, so as we work through these are things that can go hand in hand to help us understand whether or not a sequence is converging on a number or diverging. Okay, oftentimes I like to think about it graphically, and I'll say that as the terms in this case are always decreasing, yet they never ever drop below a certain value, they just get closer and closer and closer. So again, you can get that feel that they approach and converge on that value. Likewise, if our terms of our sequence are always kind of getting bigger, yet are bounded above by something, we know that they slowly get closer and closer and closer, and again, therefore the limit exists, and therefore it converges. Now, the last thing I'll leave you with is, well, because we have this new idea of being monotonic, how do we determine that? Well, there's a couple different ways depending on what you feel like doing or maybe what the expression looks like. One way may be easier than the other. So I'm just going to show you 3 quick examples of methods that will allow you, when looking at a sequence rule, to determine whether or not it's monotonic. Again, whether it's always increasing or decreasing. Now, the first one's called the difference test. Now, in the difference test, what you're going to do is basically examine one term and the term right before it. Okay, so what you can do is basically this. We can say we have the n+1 term. Okay, that's obviously a term. And then we'll look at the difference between that term and the one right before it. So again, in general, we're not using actual numbers, but in general, if we look at the n+1 term, and then we look at the nth term, and really compare 2 terms next to each other, and look at their difference, it can help us understand if the numbers are always getting bigger or smaller for any given n value. And that's, again, important to do it generally for n, not just for any specific example, because this will guarantee it works for all the terms in the sequence. So if we look at a term and the term before it, and we subtract them, if that number is going to be positive, then what we can say about it is that it's always going to be increasing. And that makes sense because obviously if the next term is always bigger than the term before it, you're always going to have a difference that's going to be positive. Because obviously this term will always be bigger than this one. That implies, in general, that we're increasing. Now, certainly the opposite is going to be true as well. If we look at a term, right, and the term right before it, and we subtract them, but it gives us a negative value, well, that means that the term before it, in this case the a sub 1, was bigger. And then this one was smaller. And if that's true for any given n value, then of course our conclusion in this case is that the sequence would be decreasing. So again, one method is to simply investigate what does the n plus 1 term and the nth term compare when subtracting them. That's why it's called the difference test. So to give an example, let's try this one. Now again, when I do my work, we're going to do it very generically. So we have to ask ourselves, what does a to the n plus 1 look like, and what does a to the n look like? So just make sure you get the idea. Let's write down a to the n plus 1 to make sure you see the difference. Now they've given us the nth term, so we can use this expression for the a sub n. We want to know, what does the nth plus 1 term look like? Really, what does it mean for the term after this in general? Well, wherever we see n's, we simply need to add 1 to that, because that's what's going on. We're going to replace the n everywhere here in the a sub 1, the a sub nth term with n plus 1. So in this case, the numerator will become n plus 1. In the denominator, it will become n plus 1 plus 1. So again, as you can see, I've replaced each n with n plus 1. And then, of course, you probably want to simplify. So this becomes n plus 1 over n plus 2. So this right here generically describes any given term in the sequence, and therefore this generically describes any term right after that. So again, what we want to do is subtract them. We want to take the n plus 1th term and subtract the nth term. If we get a positive value, we know things are getting bigger, and clearly if we get a negative number, then we know they're getting smaller. So let's go ahead and try it out. So we're going to take our n plus 1 term, so n plus 1 over n plus 2, and subtract the nth term, n over n plus 1. Now at this point in time, what we got to do is basically simplify it in some way, right? We got to figure out what's going on. Now to do that, we're going to have to find common denominators and simplify and put it all together, okay? So the common denominator between these two is obviously going to be n plus 2 times n plus 1, which means in the first term, we're going to multiply the n plus 1 times this n plus 1. Then we have to multiply n times n plus 2. And then, of course, we have to subtract it. So this is going to be n plus 1 times n plus 1. So we're going to square that, minus n times n plus 2. Okay, and again, that's just regular common denominators and adjusting our numerators. Now, if we simplify this expression, it works out to be n squared plus 2n plus 1, and then we're going to subtract n squared and subtract 2n. And then the bottom, of course, I'm just going to leave that as kind of our common denominators here. But clearly we can see that some of these things are going to simplify away. And in fact, what we notice is that the n squared and the 2n go away, leaving our numerator to just be a 1. Now remember, at the end of the day, we want to ask ourselves, what do we know about this value? Now, as remember, because this is a sequence, the terms that go in for n are only going to be positive integers, okay? So we want to think about, what do we know about these numbers, if we plug any sort of positive number in there. Well, obviously looking at this, if you plug any positive number in for n, the overall thing is going to be a positive value. So we can say right now, this is going to be this way. So because it's always going to be positive, it's greater than 0, we can say that this sequence is increasing. Now further, just by visually looking at it, if we took the limit of this expression as we went to infinity, right, or even this one right here, if we went back to the original, we could tell right away that as n becomes infinitely big, this thing here, this is approaching 1. It does converge to a value of 1. So what we know then is, because this right here is increasing, it's always getting bigger, yet it approaches 1, that means from a visual idea, we're getting bigger and bigger and bigger, but we're approaching and getting to this value 1. And that means that another kind of conclusion we can make is that all the terms of the sequence, right, they're always going to be less than 1. But more importantly, that means that while this is definitely an increasing function, we can also describe it as being a bounded function. Because not only do we know it's increasing, but because the limit exists, we know this is where it's approaching. So it's always getting bigger, approaching 1, which means it has an upper bound. Now, the second thing we want to talk about, again, as far as a method to show sequences being monotonic, would be what's called the ratio test. Now, in this case, we're still going to do the same thing we did before. We're going to examine the n plus 1th term and the nth term. This time, instead of subtracting the two terms, what we're going to do is we're going to divide them and see how big that number is and look at that comparison. So if we take the n plus 1th term and then divide it by the nth term, and that obviously works out to be greater than 1, that means that obviously this number is obviously going to be bigger than this number. So that means that in this relationship, as you get bigger and bigger and bigger, so do the numbers. So this would tell us right away that this would be increasing. Now, like before, if the opposite is true, then we definitely get the other outcome. So if we compare the n plus 1 term to the nth term, and as we divide those, we discover it's less than 1, that means the denominator is bigger, always in that relationship. So in this case, we can just say that the sequence is decreasing. So again, let's try that out. Now, I'm kind of sticking with the previous example we just did. So again, from before, the n plus 1 term on this one is going to be n plus 2 over n plus 1. So let's check the ratio. So if we take the n plus 1 term and divide it by the nth term, what that looks like is going to be our n plus 2 over n plus 1 divided by n plus 1 over n. Now, obviously, to simplify, we'll just multiply by reciprocal at the bottom and put things together. That makes n squared plus 2n here. And then, of course, n plus 1 times n plus 1 in the denominator. And I'll go ahead and multiply that out. Now, as always, we want to look at what we know about the values here. Well, in this case, obviously, the numerator and denominator are all almost identical, except the denominator is 1 more. And so no matter what value of n we plug in here, the numerator, again, will always be 1 value bigger than the value of the numerator. So because the denominator is always a little bit bigger than whatever the numerator is, we can always say that this ratio will always be less than 1. And therefore, our conclusion is that this sequence would be decreasing. Now, just like our previous example, we can clearly see as the limit of n becomes infinity, this also approaches 1. So again, just like before, because we know that this sequence is always getting smaller yet approaches 1, our conclusion also can be that this is bounded. Now, the last method we want to talk about is what's called the derivative test. So since obviously we've already had a lot of experience with calculus, and we also know that calculus, especially involving the derivatives, can tell us when things are increasing or decreasing, we can basically look at this expression, and just like I did with limits, treat it like a function, look at its derivative, and let that tell us, is this right here getting bigger or getting smaller, okay? And the conclusion is exactly what you'd expect. So in this case, if you take the derivative of our function, and by the way, what we're going to do is basically say we're going to let our sequence, right, basically be viewed as a function of n, okay, so I just want to use function notation. If we look at the derivative and the derivative is positive, obviously what we can say then is it's increasing, because obviously a positive derivative would imply that about the function. Likewise, if we look at the derivative of it and it's a negative value, that would imply, of course, that the sequence would be decreasing. Okay, so in my example here, we have a different sequence. And again, we're going to view this as saying, well, we have a function here of n, and we'll just call that function 2n over n plus 1. What we want to do is figure out what's the derivative, okay? And then figure out for values of n, is this a positive or negative expression? So this time we'll need the quotient rule. So it'll be 2 times n plus 1 minus 1 times 2n divided by n plus 1 squared. And as always, let's go ahead and simplify that. So in the numerator, the 2n's cancel, so we're just left with 2 over n plus 1 squared. Now again, what we're thinking about is, as we plug in larger and larger values of n, again always being positive, what do we know about these values? Well, obviously no matter what the denominator is, you're squaring it, it's always going to be positive. So no matter what you choose for n, it's always going to be a positive over a positive, which of course makes positive values. So in this case, the derivative, right, as I view this as a function here, is going to be a positive value. And of course the conclusion, if your derivative is positive, is that this is increasing. And again, as always, we can see clearly as the limit approaches infinity, this goes to 2. So because it's going to 2 and always increasing, we can also say it's bounded. And more specifically, we can say, just like our previous ones, it's bounded above by this limit. So this graph is always getting larger, if you will, if you looked at all those dots of all those sequence points, but bounded above by 2.